a pleasure to introduce Justin to start off the quarter. He'll be speaking about an overview of the restricted geometric language program.
All right, thanks. Thanks to the other organizers. So I will start off with kind of the everything's as usual, but first of all, I want to be seminars, and then also because I'm going to be changing coefficients and stuff a lot in this talk, I should probably be kind of careful. So for now, K will be an arbitrary algebraically closed field. X will be a smooth connected projective curve. Ground field. G will be a connected productive group. Of course, as I assume it's algebraically closed, it's not having to split. Okay, so what I'm going to do is state two other versions of kind of pre-existing versions of the geometric Langlands conjecture, categorical version that existed before the restricted story, which I'm going to talk about for the rest of the talk. And this will kind of be to orient us and to show how it fits into the big picture. So I think it makes sense to start with the characteristic 0 to Rham case, because that's mostly what we've talked about in this seminar, I guess. Before the previous quarter, even had a quarter valence of Campbell construction, eigensheaves, which is very much something that happens with the Rham situation. So let's start off with that. Okay, so I'm just going to write the symbols and then I'll sort of explain what everything means after the fact. Okay, so let's go through these things one by one. So dmod means the PG category. So everything is going to be derived kind of by default. And so when I say DG category, I mean like the big kind of DG category with all direct sums and so on. So DG category of algebraic D modules. Okay. Here we are in the BunG seminar. Module stack of D modules. Next. InsCo is the DG category of incoherent sheaves. This part I don't want to emphasize too much in this talk. If it's not something that's familiar, then just pretend it's quasi-coherent sheaves, and it's quite small. It's a slight enlargement of the category of quasi-coherent sheaves. Really, again, kind of you should think unbounded derived category. The difference between quasi-co and InsCo will only become relevant sort of very, very deep talk to get there. Here, there is a singular support condition. And again, I don't want to harp on this too much, so we'll just explain what the notation means, but probably never get back into it again for the rest of the talks, like later talks. So this is a singular support condition. Again, it looks a little bit exotic maybe because we're talking about coherent sheaves, not D modules or constructible sheaves or something like that, but there is a notion of singular support in this setting. And what the singular support condition is saying is that, well, there's kind of a natural home for singular support conditions in the setting of coherent sheaves, which is if I have a nice algebraic stack like this looks this is, I'll talk about this in a moment. it'll have this cotangent complex that's concentrated in degrees -1, 0, and 1. And so if I take h minus 1 of that, this is some basically like a vector bundle over locus, and there's a special kind of conical locus inside of here called the global nilpotent cone. And so we impose the singular support condition. So this has something to do with the behavior of coherent sheaves near the singularities of locus. And if I took this to be kind of the zero section, this singular support condition would actually shrink this down to quasi-coherent sheaves, which is strictly smaller. And then if I had like the entire thing, there would be no singular support condition. This is somewhere in between. And then finally, here, I mean the derived, although I definitely won't dwell on this talk, moduli stack of G check bundles. And I guess I should say it first, G check is, as always, the Langlands dual group. So it's the derived stack of G check bundles equipped with a flat connection. On X. So the reason it says Rham, well, we are in the Rham situation, my natural notion of local systems here is going to be a principal bundle with a flat connection. Okay.
What is roughly the geometry of this local system? As an example that we can keep in mind for.
Yeah, it's a good question. It's a quasi-compact Spartan stack. It's it looks like basically, I think it's true. It's something affine modulo G check, and it is derived. So you should think it's like it's somewhat singular, but it looks kind of like a locally complete intersection.
In terms of this stack, is it possible to say roughly what the singular support condition?
I don't want to get too into the weeds with the single support condition because it's not going to be very relevant to talk. So yeah, it'll definitely come up later. Okay, so I just kind of want to like get all these symbols up on the board so we'll have something to compare to later. And again, this has appeared in the seminar previously, but it's been a while. Maybe it's kind of glancing. So okay, for the questions about this, again, I'm not expecting everything to be familiar or everything to be even comprehensible necessarily, but I kind of want just a point of reference. Compare between the different versions. Any other questions, comments? Okay. Some remarks on this that we'll keep in mind for later is that both DG categories that appear on either side of the equivalence are themselves k-linear. Maybe it just seems like it's kind of a dumb thing to say because I mean, everything is k-linear here, but that's the point I'm making. BunG and locus, this Rham version of locus, are also defined over K. Okay, again, I'm drawing attention to the seemingly very obvious fact because this will be different in subsequent versions. Okay, and then some names. This was conjectured by the precise form of the conjecture was given by Rankin Gatescory. Following Bellingson and Drinfeld. Didn't give a precise formulation, but most of this is kind of based on their ideas. And there's a proof in progress. Sort of partly appeared, I think, but it's been announced. I won't write all the names because you thought 6 authors is bad. There's 8 of them. So it's this C. Is it? Yeah, sorry, that should be C. Thank you. Thank you. Yeah. Rankin, Beraldo, Chen, Gatescory, Fershiman, Lin, Raskin, Rosen. Okay. Check Dennis's website. Please. Okay, so that's the Rham situation. Now, in the case where K is actually the complex numbers, there's a different version of this, which is called the Betti Langlands geometric Langlands correspondence. Or I should say equivalence. Okay, and so again, I'll write the symbols and then explain what they say subsequently, what they mean, rather. And I should say Betti. Okay, so let's explain all of the notations. So first of all, what is Betti sheaves? Here, I mean all, so not necessarily inconstructible, which if you necessarily inconstructible. So again, this maybe looks a little surprising if you're used to, I don't know, Excel sheets or something. Almost always take things that are kind of compactly generated by constructible sheaves. Like that's usually how you set things up. But here we really take all of the Betti sheaves. Sheaves of cube vector spaces. And this is sort of in the analytic topology. Sorry, I hope it's legible. Crunched in there. So, okay, so just take arbitrary sheaves of vector spaces, of cube vector spaces in the C analytic topology. Okay, here, and I realize now I left off the nilp over here. It should appear again over here. Here we have this nilp seemingly the same as on the right-hand side, but in fact it's not the same, and this is a little bit mysterious, I think. So it's actually a different nilp. And I mean, okay, it's on opposite sides. We have, you know, Langlands dual groups appearing in different moduli spaces, but more relevantly, this is singular support in the sense of like constructible sheaves in the analytic topology, okay, which is completely different, or you know, quite different from singular support in the context of coherent sheaves. So this one is definitely more classical. You know, it looks quite close to the sort of singular support for D modules as well. And in particular, this is with respect to the nilpotent cone inside of the cotangent bundle of BunG, which might be a more familiar kind of object. So this is some Lagrangian inside of here. And so this looks, again, more like kind of a classical singular support condition. But notice it didn't appear over there, right? So it's something that's different here already. But again, different nilps, and not entirely clear why there's a nilp on both sides or what the relationship is between these things. I don't think anybody really knows, as far as I know. Okay.
Is there thought to be, or is it just a random coincidence of terminology, or is there actually a genuine relation between the?
I really don't know. I mean, that's, yeah. I've definitely heard Dennis say that he doesn't know them and so on. So, okay. So then, finally, I think the only thing I haven't explained on the right-hand side is looks this Betti. So this is the, again, derived stack of G-check local systems, now in the Betti sense, meaning kind of like families of representations of the usual topological fundamental groups, the G-check local systems on the kind of Riemann surface attached to C with rational coefficients. And again, this thing assembles into a moduli stack. I'll say a word in just a second on kind of what the relationship is between these two moduli stacks. So we'll just come back to that momentarily. Any questions about this before I? Yeah.
Is it correct for that with the right hand side only depend on the genus first, whereas
Yeah, absolutely. It only depends on the homotopy type of this Riemann surface, right? And that's totally unclear about the limits. So that's something I'm just going to write next panel. But yeah, it's a very good point, right? This only depends on the homotopy type of this thing, not even its complex envelope structure, right? Okay, so let me again make some observations. So just kind of in the same vein, we should be careful about coefficients so we don't get confused. So both DG categories are Q linear. Sorry?
When you say local systems, what are the coefficients? Q.
Rational coefficients, yeah. Just local systems of Q vector spaces in the most classical sense. We just have to say it in families. Okay. So it'll be, as I'm about to say, it'll be an algebraic stack over Q. So so here, as always, BunG is going to be defined over the original Granfeld K, here C, right? And locus Betti, on the other hand, can people see if I write over here? Okay, on the camera.
at a count two, yeah.
Okay.
It'll eventually come behind the speaker.
Let's see if this is that okay?
That just at the cusp. yeah.
Just barely okay. Okay, I'll keep that in mind. Okay, so this locus Betti is defined over Q. So this is something where I can define a family of such objects parameterized by any Q algebra. And finally, as Akil pointed out, this locus Betti only depends on the homotopy type of X of C. Hence, really only depends on the genus of X. So this would imply in particular that the left-hand side of the equivalence, the Betti Langlands equivalence, only depends on the homotopy type of X, which is super unclear and surprising in a way. Okay, some more comments. This was first proposed by Bensby and Nadler. And it does follow, in fact, from the Rham case. Using Riemann-Hilbert, although be a little careful because there's some subtlety here. So this line of argument will pass through the restricted equivalence that I have introduced. The reason is because of these non-inconstructible sheaves that are appearing on the left-hand side, right, or something that are not part of the Riemann-Hilbert correspondence. And so there'll be some restricted version where the Riemann-Hilbert, where everything is inconstructible, and we'll be able to make some argument that kind of restricted to Rham implies restricted Betti using Riemann-Hilbert, and then you somehow deduce the Betti equivalence from the restricted Betti equivalence. Right? That's kind of neither here nor there. But I would just point out that this work in progress by the 8 authors would imply the Betti as well. Apply that. Okay, and then the relationship between the two versions of Loxis. I realize I'm writing LS and saying Loxis, but it's easier to say Loxis than local systems, so I'll keep doing that. So the relationship between the two is that they're isomorphic as C analytic stacks, kind of again by Riemann-Hilbert. So you can write down some complex analytic isomorphism between them. But they're definitely not algebraically isomorphic. Just because the Riemann-Hilbert correspondence isn't algebraic. Generally speaking, probably they're the same in genus 0, but outside of that, these will be different. I think they're probably genus 0. All right. Questions about Betti? Okay, so we see some, parallels here between, the story of Rham cohomology versus singular cohomology, that type of thing. And then the third sort of setting that we would want to consider would be Campbell cohomology. And that's what I'm going to talk about next. Yeah, so what about an Natal version? What would that even look like? It's not super clear, which is the reason why this took so long to appear. So here you would have arbitrary algebraically closed field, right? In particular, allowing characteristic 0 and characteristic p, positive characteristic, unlike the previous two cases. You would want, a tau bar sheaves in local systems. Like this. Okay, so why would we? Well, okay, one reason is that we would want something like this. Is just it looks like parallel to what appeared before, the Rham, Betti, now Tau, right? But there are kind of arithmetic reasons to care about this. I think probably most of my talk is going to be occupied with. So if I take in particular k to be f bar, so back to the kind of original motivation for the Ital topology, even x naught and g naught defined over f cubed. Okay, so of course I can base change these to f bar, and they'll be my x and g from before. I'm assuming that they're defined over a finite field. So then there is an arithmetic version of Langlands correspondence, right, that preceded the categorical one. I mean, maybe, I don't know if you would object to my use of arithmetic here, but I mean, for a global function field, a positive characteristic, right? Conjecture or kind of the group G naught, we could think of it, if you like, as a group over the field of rational functions X naught, which is global field of positive characteristic. And therefore, kind of Langlands' original program applies to it, right? So the hope is that we can extract some arithmetic information from a potential Ital geometric Langlands equivalence. And this is really inspired by the kind of earliest work on the geometric Langlands program by Drinfeld, where he used exactly this idea to construct the first examples of construct automorphic sheaves, and then automorphic forms by taking trace of Frobenius. So like many, probably most things in this talk, this is ultimately Drinfeld. So automorphic forms should kind of arise as the Frobenius trace. Of automorphic sheaves. Automorphic sheaves, so meaning, well, kind of whatever objects appear on the automorphic side of this Eiffel geometric Langlands equivalence, so there'll be some kind of sheaves on BunG. Probably with a Frobenius structure, right? So something like these sheaves on BunG. These are the types of things that we can take to Frobenius trace. So ideally, we would be able to construct Hecke eigensheaves here, and therefore get automorphic forms by taking the trace of Frobenius. But this Eiffel version would also give us something better. So this would kind of give us a perspective. We'll see it does in fact give us kind of really kind of a refinement of the original Langlands conjecture for the for a function field. So it'll give us kind of an interpretation, in fact, not just of eigenforms, but of the entire space of automorphic forms, which is something we do. Okay, questions? So now I'll state the restricted equivalence next. Well, some substandard level of detail. Yeah, so maybe I should have said like eigenforms or something here. Right, because that was kind of the original formulation, it's just that you can match up eigenforms with local systems. So they should match up, they should come as trace of Frobenius of some kind of eigensheaves. Okay, so back to arbitrary or algebraically closed Rham field. So the 6 authors, I guess I should say it once. Rankin, Gatesbury, Kashdan, Raskin, Rosenblum, Borshowski. Conjecture the following. This will be what I'll refer to as kind of the restricted geometric Langlands equivalence. Okay, and it looks as follows. So the automorphic side is, in fact, well, almost the same symbols I wrote as in the Betti situation. In particular, we have this nilpotent singular support appearing on the automorphic side, and the spectral side is going to look familiar as well. The new gadget that appears here is this so-called restricted G-check local systems with restricted variation. I'll comment a little bit more on what this thing looks like, but part of what I want to do in this talk is sort of take as a black box the existence of such a thing, okay, and see what kind of consequences we can draw. So, okay, first of all, what are these symbols in this case? So here, sheaves is going to mean, again, DG category of now inconstructible, because I really don't think you want to consider anything else in the Eiffel setting. Inconstructible Eiffel sheaves of QL bar vector spaces. Just say with QL bar coefficients. Right? Here, same as before, but with the caveat that I'm using here the theory of singular support for Eiffel constructible sheaves, which is something that came after these other notions of singular support. So this is due to Sasha valence and following, I think, Saito.
The difference between this category and the previous category is the topologies. How is that?
It's all, and then also I only consider inconstructible. Which again is the only thing I think you would want to consider in a detail setting, right? Whereas here there were some weird non-inconstructible Betti sheaves. I don't really understand why these things they do, but here everything's inconstructible as you would hope. Okay. In particular, like the compact objects here will be just usual construct.
If you consider only the inconstructible ones for the bad things, what you get unramified? That's possible.
Yeah, definitely. So in that case, that will match up with the kind of, I think that matches up with the restricted thing on the right hand side. Yeah. So inconstructible in the Betti setting on the left hand side matches with, there'll be some restricted Betti thing, and it'll match up with that. Okay. So this looks analogous to something. You can make a similar looking kind of equivalence in the Betti setting as well. I'll come to this. Okay, so this is sort of, again, this same flavor of singular support that appeared in the Betti setting on the left-hand side. And then finally, there's this looks restricted, which again, I won't define precisely in this talk, but just to say what kind of thing it is. In some ways, it's kind of like the other versions of Loxis, but in some ways it's not. So it's a DG stack of G-check local systems. With restricted variation. That's what restricted means. So again, I'll make some kind of limited remarks about what this thing actually looks like, but I mean, they're really well-known obstructions to making the kind of moduli space that you might really want in your heart in this setting, right? Something that looks like the Rham or Betti situations. So, there's this whole theory of, deformations of Galois representations and so on, right? And so, in fact, this thing is going to have some sort of formal directions to it. So it's going to look not just like an Artin stack, but sort of like a Artin stack with some kind of formal directions. And it's going to have tons and tons of connections, unlike, say, Loxis, Rham, or Betti, which are sort of often connected. The restricted version will have many connected components, which is you can see as sort of a deficiency, but I think in a sense it's the best we can do in the Betti in the Ital setting. We can get quite a lot from it. And sorry, I should say, dual local systems. Local systems, dual bar coefficients, of course. So more remarks. So in this case, in getting our coefficients straight. So both DG categories are dual bar linear. And the equivalence is as such, right? And sort of like the Betti case, BunG is going to be defined over whatever the ground field was. It was arbitrary algebraically closed. And this Loxis restricted will be really something over QL bar. Good. So something about this Loxis restricted that's different is that you can make sense of this thing really kind of in any sheaf theory, kind of in a reasonable sense. So in particular for the kind of Rham and Betti sheaf theories. So this both the stack and the above equivalence makes sense. Let me not try to make any formal statement here, but just in other sheaf theories. So in particular, the kind of ones that appeared previously. including Rham, meaning I should say D modules, I guess, including for D modules. And Betti sheaves. All you really need is kind of like the usual properties, functorialities you would expect from a sheaf theory. And in particular, it's really important that you know what like these objects are, like kind of locally constant. So there are some implications as well. I think I alluded to it earlier. So these restricted statements are inversions where we have kind of quote unquote full geometric Langlands. These are going to be a priori weaker. So there'll be a restricted version of the Rham geometric Langlands that again follows from the full version for relatively straightforward reasons. And then likewise in the Betti setting. But in the étal setting, restricted is all we have. As far as we know. If you look in the proof of geometric Langlands preprints, you'll see that they claim that there are kind of converse equivalences as well, but it's sort of a warning that that takes some other like very serious input as well, right? So if you take restricted de Rham geometric Langlands and you know that the geometric Langlands, kind of full geometric Langlands functor exists with some nice properties, you would be able to deduce that it's an equivalence, but you need the functor, which is something very trivial. So I wouldn't say that the converses are sort of topological or anything. Okay, so let's write just the kind of fixed notation. E will be the coefficients of our sheaf theory. Whatever it is. This is split into three cases, right? For the cases that we actually talk about. So for the Rham, it's just E equals K. For Betti, it's E equals Q. I mean, you could take any Q algebra, I guess. Doesn't really matter. And for étal, it'll be field R, l-adic coefficients. Okay. Okay, let me make a quick comment on, I won't have too much else to say about this Loxis restricted in this talk. Again, I want to kind of black box it, but let me make a quick comment about the relationship between Loxis restricted and the earlier versions of Loxis in the settings where we can compare them, right? So Rham and Betti. Okay, so whatever this Loxis restricted is, it's going to canonically map to sort of the full Loxis in the Rham or Betti settings. Let me just say question mark. Question mark between Rham or Betti. in both cases, it's a closed embedding at the reduced level. So like I said, this has some kind of formal stuff, some formal directions, but if I ignore that, this will be a closed embedding. At the reduced level, and it's even bijective on equivalence. Okay, so if you're having trouble imagining what such a thing could look like, let me just say in words something more precise, which I know is valid at least in the Betti setting. And let me not try to write it on the board, just for the sake of time. So at least in the Betti setting, what this Loxus restricted is the following. So Loxus Betti maps to kind of its own coarse moduli space, which parameterizes semi-simple local systems. And the map is like, take a semi-simplification. Turns out that that moduli space of semi-simple local systems is really the coarse moduli space of this thing. And so what this Loxus restricted is in the Betti setting is it's the kind of the union of the formal completions of all of the fibers. So if I take all the local systems with a fixed semi-simplification, okay, that'll be some closed substack inside of here. Its formal completion will be kind of a component in here. Okay, so this looks like some gigantic disjoint union, right, over all of the kind of semi-simple local systems of the each of those components will be the formal completion of the moduli of all local systems with that semi-simplification. That's kind of the flavor of it. So you see it kind of like pulls apart the Betti thing into like many pieces. So it looks like kind of a silly thing to consider in the Betti setting. But again, in the Intel setting, it's all we have. And there's also this kind of interesting observation. I think we're talking about, we're in the Betti setting, kind of having a sheaf on Loxus restricted will correspond to the thing on the automorphic side being in the I won't have too much more to say about Loxus restricted in the talk. Like I said, I'll kind of black box it. So let me just end this segment of the talk here. Any questions? Oh, this kind of orientation. No? Okay. So what I want to focus on basically for the rest of the talk is, let's say we had this equivalence, or maybe not even, I'll explain there's some unconditional results in this direction already. And in this kind of formulation, what does this actually bias in the context of working over, in the context of geometric Langlands over a finite field, right? In particular, what kind of arithmetic consequences can be deduced? This is what I'm going to focus on. And I just want to say, just to kind of set the stage, like, since I'm not going to talk about this Loxus restricted so much, the real key input in the results that 6 authors prove unconditionally is really just some kind of representability type statements about Loxus restricted. Okay, somehow this is like, takes some work, and then once you have this, lots of things follow more or less formally. This is something that's new and you know, we're able to get quite a lot of advantage of. Okay, so next part of my talk will be the trace of Frobenius. So besides this Loxus restricted, the other main new idea in these papers is the so-called categorical trace of Frobenius. So let me introduce an instance of this as follows. So C, so this will be some abstract nonsense for a moment. C is going to be a DG category over E. I guess this could be, you know, any field, but I'm thinking Betti, right? F is going to be an endofunctor of C. Then all functors, since we're in this setting of kind of DG categories stable under direct sums, the functors will be assumed continuous by default. Okay, and then we also assume for the construction I'm about to make that C is dualizable with respect to the Lurie tensor product, we need the categories. Just its natural tensor product that exists on equivalent categories. Okay. Okay, so then we can make the following construction. There's a trace attached to this data. I'll call the trace of f acting on C. And it looks as follows. First of all, f determines a functor from vect. And again, this is vect over E, just to be clear. To endofunctors of C, again, all continuous by kind of default, right? So this vect picks out the functor f, it just sends kind of the scalars, right, the generator here to f, and everything else is determined by continuity. This is isomorphic to C dual tensor C, right, by kind of abstract nonsense because C was assumed dualizable. And then finally, I can evaluate and end up back at the unit, which is vect. Okay. This is something that makes sense in any symmetric monodal category, in fact, right? All I've used here, right, is that I have an endomorphism of a dualizable object in a symmetric monodal category, completely formal. And what I got, right, was an endomorphism of the object category vect, continuous endomorphism, okay? And that's just going to identify with a vector space because such an endofunctor is determined by, again, what it does to the distinguished generator. Okay, so this trace is really a complex of vector spaces. Okay, so to this data, I attached a complex of vector spaces by this totally formal construction. And I could do something similar, as I said, in any symmetric monodal category. The only caveat is then all I'll get is just an endomorphism of the unit object. That's kind of all I can say. Okay, and this has a natural functoriality. Okay. So let me kind of just set up the functoriality without explaining it in too much detail. It's really some abstract nonsense about two categories. So first, I have two such DG categories, C1 and C2, and I have endofunctors of each of them. Okay. And suppose I have a functor T from C1 to C2, which has continuous right adjoint. It's the technical condition we need here. So for example, if C1 is compactly generated, that's equivalent to saying that T preserves compact objects. Okay, so it's not always satisfied, but I do need that condition here. And then the last piece of data that I'll need for this functoriality is a natural transformation alpha, which goes as follows from T compose F1 to F2 compose T. So I guess this is a natural transformation of functors from C1 to C2. So suppose that I'm given all of this data, then by, again, some formal nonsense, I get a linear map, okay, which I'll call trace of T comma alpha from the trace of F1 acting on C1 to the trace of F2 acting on C2. Hopefully this is believable, even if we don't see the mechanism right away, it's something very formal. I was doing this kind of for ordinary, meaning like 2 comma 2 categories as opposed to infinity 2 categories would be an exercise, but it's harder than that. This generality.
So this F, the F appears, so F defines a functor from vect to NC. Is sort of tautologically, it must be tautologically equivalent to a map, an endomorphism from C to C, or a map from C to C.
Yeah, because again, I'm saying it's a continuous functor from vect into any GG category is the same as just specifying an object, right? Because I just have to specify where the generator goes and everything else is determined by vect is kind of freely generated by its just E, right? One-dimensional vector space E. Okay. Okay, so now let's apply this abstract nonsense in a more interesting special case. So why not is going to be a Artin stack locally of finite type over a finite field Q. Okay, and so I'll stick to my usual convention of like I get rid of the not by base changing to FQ bar. Okay. So then this Y carries a distinguished endomorphism, which is the geometric Frobenius. So this is the thing that if I start with Y naught, right, kind of locally on Y naught, this looks like raising to the qth power on functions, right? That gives me an endomorphism of Y naught. And then by functoriality, I get the corresponding endomorphism of Y, right? I always get these Frobenius confused. I hope I'm saying this correctly, but I think it is correct. And that yields, therefore, an endomorphism of the category of quasi-coherent sheaves, just say by direct image. Now, okay, you may say, why is direct image a reasonable thing to consider here? Well, I could do the same thing for inverse image, and that would definitely be okay. And then the point is, this is actually an equivalence. So one reason that this is justified to talk about the direct image is to say, well, the inverse image functor induces an equivalence, therefore, it has a right adjoint, which is its inverse, and that's Rham lower star. Okay, why is it an equivalence? Okay, this is again something that I always forget every time I don't think about this stuff for a while and then have to relearn. The reason is because the same endomorphism of the category of sheaves is induced by the kind of Frobenius twisted automorphism, where I just take the kind of geometric Frobenius acting on FQ bar, right? And that actually agrees with this endomorphism. Therefore, it's not. Does this ring a bell for anybody? I think the last time I heard someone explain this was maybe in Ginsburg's class a while back about linguistic brackets or something. So, okay. So this is some standard stuff in finite field world.
Like, it only depends on the perfect seed. It only depends on the perfect. I mean, the sheaves on Y only depends on Y.
Exactly.
And then on the perfect seed, literally another.
Correct. Exactly. Yeah. So I said, like, if I take this geometric Frobenius acting on FQ bar, like literally the Frobenius on FQ bar, maybe it's inverse, right? That gives an automorphism of Y, but it's not as an FQ bar scheme, right? It's rather twisted, so it kind of lands in the Frobenius twist of Y. But then the sheaves on Frobenius twist of Y are canonically the same thing as sheaves on Y, right? So that's in the background here for sure. Other questions about that? Okay, so I'm going to apply the above formalism in this case. So it turns out, just basically in total generality in this étale world, the sheaves on Y are going to be compactly generated. This is something that we didn't get for free in the Rham setting. We had to sweat a lot about it, right, for things like BunG. But in the étale setting, everything is kind of automatically compactly generated, these types of categories of sheaves. And the reasons is because essentially because we have Schritt push forwards in all cases. And so certainly on an Artin stack, this thing will be compactly generated formally and therefore realizable. Okay, and so that means I can apply the above formalism and get a QL bar vector space by taking the trace of this endomorphism, actually automorphism, acting on the category of sheaves on Y. So it'll be a complex of QL bar vector spaces. Just produced by some abstract procedure, not at all a concrete thing, right? It's okay. Apply the above formalism in this case. Okay, let's investigate this further. How am I doing on time? Let me see if there's a natural stopping point anytime soon.
You're sort of in the vicinity of the break.
Yeah.
You did start 5 minutes late.
Right, okay, let me go a few more minutes and I'll try to find a natural stopping point. Okay, so now I'm going to make use of this functoriality to, again, to kind of relate this to some more familiar objects. So in particular, there's this classical trace of Frobenius construction that I mentioned earlier, right? So let's say I take a compact object and sheaves on Y. So at least if Y were a scheme, this would just be an inconstructible complex. I think in general, this is a bit more restricted than that. But morally, you should just think this is a constructible complex. And let's say I have a base structure on it. Sorry, that should be Frob. So I'll call this base structure alpha. So I actually don't need this to be an isomorphism, which is what we would typically call a base structure, right? So I actually only need an arrow like this, for what it's worth. So we'll always have such a thing. For example, if F comes from a sheaf on Y naught, right? Then we would actually have a strict base structure. So that's typically where these things arise, but you can also consider other base structures. Okay, now we'll apply this functoriality principle in the following case. Take C1 to be vect, C2 to be sheaves on Y, F1 is going to be the identity on vect. F2 is going to be this automorphism of the categorical sheaves for lower star that I took the trace of over here. And this T, well, to give a functor from vect to sheaves is really the same as to specify a sheaf. Let me just write it as a functor just to be super clear. So it's going to be the functor that's kind of determined by F, right? I fixed this F. So that determines the functor will be given by this one, right? From vect to sheaves. Now, the hypothesis that F was compact is exactly the hypothesis I need for this hypothesis that T has a continuous right adjoint to apply, right? Because that'll say that then this functor preserves compact objects and therefore has a continuous right adjoint. So that's why I needed to assume that was compact. And then finally, as the notation suggests, alpha is going to be this lax base structure. So if you parse out what kind of a map, what kind of a natural transformation alpha is, well, it's a natural transformation of functors from vect to sheaves, which is really just the same thing as a map, right? If I evaluate on the generator here, and if you think about what that map is, it's exactly going to be a map like this. So I claim this precisely fits into that abstract setup. Okay, and then finally, what we get is what's called in the 6th author paper the class of F comma alpha. And by definition, it's this trace of T comma alpha, right? That I stated earlier as a functoriality principle. And so by definition, it is an object. So by definition, it'll be it'll be a linear map, right? From the trace of the identity functor acting on vect, but that's just the vector space scalars, in fact. So this is actually just going to be an element of the trace that appeared at the bottom of the board over here. So this trace of Frob lower star, I hope I don't go off the screen here. So this kind of trace that I said earlier, it exists abstractly. Whatever it is, it's some complex of vector spaces. So what I've just explained is that if I have a sheaf with a base structure or even a lax base structure, I can produce a vector in this vector space. So it behaves a little bit like you would, it's kind of this universal recipient for traces of Frobenius constructions. Okay, maybe that's a decent place to stop, so. Take a break.
Potentially
Questions?
cover your ears. Oh, actually. Less. So that we found out, we just gotta be aggressive with the master point.
Okay, so it wasn't the most natural point to break, but let me just remind us where we were. I pointed out that if I have a sheaf on Y with a base structure, or a lax base structure even, I can produce a vector in this mysterious trace vector space. Okay, it's categorical trace, which is a kilobar vector space. Okay, and now that's kind of one way to relate this to more familiar things, and let me explain another way to relate it to something more familiar. So not only is it sort of a natural recipient for Frobenius trace, it's also kind of a natural source for producing functions by the Frobenius trace instructions. That's what I mean. So there exists a natural map, and for reasons that I don't entirely understand, they call it LT. I think it stands for local term. From this trace, categorical trace, this vector space, to following vector space, compactly supported functions on the FQ points of Y0. And so here this means compactly, which, I mean, this is some like abstract groupoid, right? So like that really just means finitely supported. Supported QL-bar valued functions. Okay, so this is kind of where you would expect Frobenius trace to land, right? And in fact, this is compatible with the previous construction in the sense that you might guess if you thought about it for a moment. So it's going to have the property that this local term, if I apply this to the vector in the trace, categorical trace, right, that came from a sheaf with the base structure, this is going to be the function attached to the base sheaf by the usual trace of Frobenius construction. Is a function response. Okay. Let me not justify this, although it'll actually be written in the notes, but it's again just kind of a formal application of this functoriality procedure. Hopefully that's a believable statement. Okay, so there's also a way to go from vectors in this categorical trace vector space to actual functions. Okay, questions about that? Didn't explain it.
Sorry, is the data in the first thing from push star, or is it this alpha? Is it?
In this thing?
Yeah, so this should be the trace of Frobenius, right? But
Yeah, this is the vector space. This is the categorical trace of this endomorphism of this dualismal category. This is a vector space. This is also a vector space. This is a linear map.
Oh, okay. Sorry.
Very
I was
confusing.
now I see.
Yeah.
First time it's the complex, right? It's the right pattern. Second one's
Correct. Yeah, that's absolutely right. So this is the classical vector space, but nonetheless, yeah, we do have this map. Okay. True. Okay. Oh, and by the way, the reason it's finitely supported functions is, well, just because I didn't assume that Y was quasi-compact. If it's quasi-compact, then of course that groupoid will itself be have finitely many connected components, and so that'll be no condition. But generally, for a non-quasi-compact scheme or stack, you write it like BunG, which you care about, right? You write it as kind of a filtered union of quasi-compact things, and you sort of extend from that case. You'll get things that are finally supported just by construction. So an important remark to make here is that this local term map is usually not an isomorphism. But disappointingly, really nice, but so this is related to the failure in the l-adic setting, right? There's a map from the tensor product of the category of sheaves on Y with itself to the category of sheaves on the Cartesian product of Y with itself, which is just using the box product, external tensor product, right? And in the l-adic setting, it's typically not an isomorphism, right? Once I should say. So my understanding, at least, is that the failure of local term to be an equivalence is very, very closely related to this. Okay, and a sufficient condition for both this map to be an equivalence and for local term to be an isomorphism is that we could write this Y again as kind of a filtered union of quasi-compact things. And these yi's, well, let's say, okay, so I'm being a little bit sloppy here with the Frobenius, is probably do again. So what I want to assume is that these things come from, yeah, sorry, it's okay. So basically, if I take the groupoid of FQ bar points here of yi, is that called find FQ bar, that this groupoid has finally many connected points. This is a very, very strong condition. Right? Like, this is the kind of thing that can really only happen for a stack and not so much for a scheme, right? Unless the scheme is like or a finite set or something, right? Because I'm talking about something like, for example, a flag variety modulo the action of the rel on the other side, or something like that. This type of stuff, where that's finally many geometry. Okay, but in our sort of case, this will, for Y being BunG, which is the case we really care about, this will hold essentially only if XSG is 0. In which case, BunG actually is like a kind of union of open substacks, each of which has finite points. Okay. Away from that case is just typically.
So it would be true for something like BG.
Yeah, definitely for something like BG, or more generally for something that's like G mod B or something like that.
I think pointy stick.
Yeah. Yeah, such things do, or yeah. A1, like but vector space mod GM, yeah, that's it. But this is typically not what BunG looks like for hierarchies. Okay, so now we're going to specialize. In this case, Y equals BunG. And okay, so say one, I should say 6 authors show this category of sheaves on BunG with singular support. This is the first place where the singular support condition would be talked about randomly detailed way. So that this subcategory is compactly generated. That's certainly not obvious a priori. If I'm not mistaken, this conclusion has a nice right adjoint, but it's not so clear. Like it doesn't have a nice left adjoint, so it's not so clear that it's compactly generated. Hence realizable, right? And stable under the Frobenius automorphism. It's just a general thing about singular support. And so therefore it makes sense to apply, again, this general nonsense and obtain categorical trace of this morphism of sheaves nil. Some complex of vector spaces a priori. Okay, and then we get to the first big theorem, unconditional theorem, not dependent on the big conjecture. Which is that this vector space is actually well, in this case, local term kind of does produce an isomorphism with the caveat that we impose this nilpotent singular support condition, right? So the local term, it lands in, compactly supported functions on the FQ points of BunG. It's going to be an isomorphism when I restrict to the sheaves with nilpotent singular support. And the right-hand side is really, I'm not writing a knot or anything. The right-hand side is definitely something of arithmetic significance. This is exactly the space of automorphic forms for this global function field. Unramified, always unramified in this seminar. So very closely related statement is that this tensor product formula, right, that I wrote up there, it does actually hold, again, for these sheaves with nilpotent singular support. So I guess what you can take away from both of these statements is that if I impose this nilpotent singular support condition, then somehow this category of sheaves actually kind of does behave like sheaves on something with a discrete set of isomorphism classes. Which again is a bit mysterious to me. It's not like these types of statements are, sorry, BunG. It's not like these statements are proved in some kind of general geometric framework. Like it really heavily uses the Hecke action thing, things like this. So it's something very special.
And again, this is nilpotent code.
Correct. Yeah, maybe they're both called the nilpotent code. I'm not sure, but it's the one that lives inside the cotangent bundle of BunG. Yeah. It's the more classic kind of singular support, except we are in the Intel setting.
In theory, that was covered in talk before Ginsburg in the very first one.
Oh, really?
Yes, mentioned it.
So it's actually going to be talking about other questions. So that concludes part 2 of the talk. So now I can read, which is the real arithmetic consequences. So far, I haven't really deduced anything arithmetic, right? Because I just said I can produce something arithmetic by some abstract procedure, but of course I haven't actually said anything substantial about it. So what is this stuff actually bias? Well, certainly you get something from the restricted geometric Langlands conjecture itself, but actually we can get something unconditional, okay, from another unconditional result that was proved in the 6th author paper. So expected decomposition. So here we're getting into this arithmetic stuff eventually. Right? So first of all, just as a little reminder, if I take any k point of x, and I guess do I want to say here, yeah, this actually here I can be back in the setting of k bar arbitrary. So let me just say that. Just for a moment, and we'll come back to the final case. Okay, so if I have any k point of x, then geometric Satake I won't bother stating it precisely, but what it actually buys us, okay, is an action of the category of algebraic representations of the Langlands dual group. So this is like, again, viewed as an algebraic group of root-dual bar. I can consider it algebraic representations. Will act on the category of sheaves on BunG by Hecke functors. Okay, so this geometric Satake equivalence tells you the representation of G check corresponds to some IC sheaf on the valence and Grassmannian, and you can use Hecke correspondences to produce endofunctor. The category of sheaves on BunG. It's compatible with the tensor product and really does specify an action. So so more generally, we can do this allowing the point x to vary, or even allowing kind of several points which can collide. So sort of using the valence and Grassmannian, right, where I allow a finite set of points instead of just a single point. There's also a version of geometric Satake in that situation. So we have functors as follows. I'll be here. So what this actually buys us is the following. So here I is going to be an arbitrary finite set. Okay, I think I wrote that correctly. Okay, so I don't really want to go into too much detail, but I'll just say if you perform this construction of this Hecke action, okay, allowing several points, and again, there's this version of the affine Grassmannian and the Hecke stack that live over x to the I, it'll exactly produce, if I have kind of an I tuple, right, of G check representations, I can put that on the valence and Grassmannian. I can use this Hecke correspondence, which actually the kind of other leg will land you on BunG times x to the I if the points are moving. So this is really the kind of natural home. Okay. And so this is sort of for any finite set I. And it'll have kind of some natural compatibilities as the natural compatibilities as the finite set I varies, which is related to the symmetric modal structure on RefG. Check. Let me just sweep that under the rug. Okay, and then there's this. I don't really know if this was anticipated widely before they proved it, but there's this result of Nadler and Yun that says that this Hecke action, it sends following subcategory. So if I take the sheaves with nilpotent singular support, okay, that'll live as a subcategory inside the left-hand side. And it sends this into sheaves with nilpotent singular support tensor. Okay, now instead of writing sheaves on the product, I'm going to do this kind of manipulation, which is generally forbidden, which is the whole point of the theorem is that we are going to be able to do this. So I would write sheaves on x to the I, but I can actually do better. So it'll actually land on sheaf nil tensor ins least sheaves. Okay, so you should think of the case, for example, where we actually have a Hecke eigensheaf, okay, which it'll turn out will live inside of here. And so in that case, right, you're going to get the original Hecke eigensheaf box product to the local system, which is its eigenvalue, and that thing is least, right? So I'm saying for nilpotent singular support sheaves, they're going to behave kind of like this, but typically, you know, these things could be non-compact or something. And so typically you'll get something that's kind of in the least here. And one little caveat is that technically this is not quite the right thing. You have to tweak this, but it only matters when x has genus 0, so we just completely ignore that. So if you look in the book in the paper, there's this stuff about quasi-least sheaves. Let me just completely ignore it and just think about end least sheaves because that's more comprehensible. Okay. Yes, thank you. Yeah, I'm just thinking again about the case of the Hecke eigensheaf. Single, you know, I. Okay, so this allows us to kind of, this is a key point, right? It allows us to kind of get around this failure of the kind of categorical code formula, the thing we want. So, in fact, there's sort of a converse to this. So again, this is new in the sixth author paper, which says something sort of converse to this holds. So if I start with the sheaf on BunG, and it kind of behaves this way under Hecke functors, right? So it has the property that when I act on it by some element of rep G check, okay, it lands in this tensor product. So you should think this kind of means that it decomposes as an external tensor product, right? Of something in on BunG times something in lease. Then it has nilpotent singular support. This is a really key technical point. And I guess, yeah, it's technical, but it's definitely key. Okay. So it has nilpotent singular support. So again, maybe a little bit hard to see why this is relevant right now, but one corollary that maybe is more immediately interesting.
Yeah. Wait, the product is also that in sheaf, no? One sheaf? Or does there?
Yeah. In here?
Yeah.
No, I don't require it. It'll happen automatically. I don't require it. The point is that it lands in this tensor product, which is definitely smaller than that sheaves on the product. And also, again, it's end least smallest factor. So both of those things make it smaller than like the tensor product of sheaves on BunG, tensor sheaf on x. It's really a whole subcategory. Okay, and so in particular, as a corollary, you get that Hecke eigensheaves, right, which definitely have this property because they'll be, when I apply Hecke functors, I'll get something, I'll get F box product, the eigenvalue, sort of, well, the local system attached to B and the eigenvalue, which will be in least. So Hecke eigensheaves have nilpotent singular support. So that's one immediate corollary. questions about this. This is like probably the most technical to talk, but it's going to be really important, so we do want to emphasize it right now. Okay. So this property, sorry. Thank you. Yeah, thank you. This is for any V in Rep2 check. Sorry. Yeah, for any V in Rep2 check, it's enough to do it for like a representative irreducibles or something, right?
Is it correct to send the map from like the tensor product to the whole sheaf on the product is not an equivalence, but is it fully faithful?
Yes, it is correct. Yeah, that's why I say like full subcat. When I say
Oh,
sends it into, that's a statement. You know, I'm not asserting the existence of a construction. It's really a statement. Right? It'll actually be fully faithful embedding. So yeah, both of these will. This will embed fully faithfully in the left-hand side of that map. This will embed fully faithfully in the right-hand side of that functor. Okay. So sometimes sheaves with this condition, the hypothesis of this theorem, are called Hecke, I think, in the paper. And so the statement is that Hecke, Nadler-Yoon says that nilpotent singular support implies Hecke, and this theorem says that Hecke implies nilpotent singular support. I mean, modulo some details about either. Okay. Now, if we apply this theorem of Nadler and Yoon, so actually I won't use the converse theorem right away, and apply some abstract nonsense, which I think is itself also due to Greenfeld. So many other things, this idea that if you have this type of structure, this type of property for the Hecke functors, it's proved rigorously in 6 author paper, it proved that this induces an action of kind of the, it looks sort of like the category that appeared on the spectral side of the restricted Langlands equivalence, but here I just take quasi. Okay, this will act on sheaves null. Okay, and so first of all, this would be expected, right? As a corollary, if we knew the equivalence, you would expect that the equivalence would be equivariant for the action of, well, what am I saying? If we had the equivalence, this acts on INSCO, and therefore it would act on this as well. This is true unconditionally. Now, there's a little funny business here in this proof. Like, they prove this in the Betti setting, right? That if you have this type of statement in the Betti setting, there's some abstract nonsense that will give you this type of action, and then they actually deduce the étal statement by some reduction from characteristics here, which is sort of unpleasant. And they say in the paper there should be like a more natural formal type of statement. They just prove it there, so I don't really have a sense of how hard that is to do. They state some kind of more general conjecture along these lines. The thought is that it should be something fairly formal, like a Tanaki paper. Yeah.
So if you have like skyscraper sheet, then the action of that skyscraper sheet will be something.
The skyscraper sheet will exactly correspond to the Hecke eigensheaves. Exactly. Yeah, that's definitely one that's for geometric equivalence. The skyscraper should correspond to, I think it should correspond to like kind of distinguished eigensheaf that I.
The skyscraper sheet should give an operator, should give an endofunctor on the right hand side.
Oh, I see what you're saying. Yeah. So right, but I guess what I'm saying is it'll. Yeah, it's an endofunctor.
Yeah, I guess
Well, that'll come from, there's gonna be some kind of maps from like if I take an I-tuple, let's say I take a single point of the curve X, right? This will then have a map to like BG check, which is take the fiber at X. And so that'll give me a functor for BG check to this thing. And so the idea is I allow the point to vary and I allow like all possible finite sets and families. That'll kind of assemble. So like in the Rham situation, you get this by sort of integrating over the Rham space. And it's also known in the Rham setting, although it's seems to be somewhat deeper and the proof uses localization. It's very Rham in nature. This looks different, but you get a similar result in the end. But very important here, right, that we only get the action on sheaves.
For quasi-color local systems that each have that.
Correct.
In terms of representation.
From the data of all of these, so specifically functors from here to here, okay, compatibly assigned varies. That should assemble into an action. Then in the Rham setting, you can kind of sort of see. So right away, this gets us something really striking. It's still not, maybe not exactly arithmetic, but getting closer. So geometric observation is that if I have two local systems, and I'll write restricted. This is well, do it in general. These are just kind of actual local systems, right? Close points in the stack. So if these have, and this I sort of alluded to earlier, I think I said it out loud. If these have non-isomorphic semi-simplifications, which I think has an obvious meaning, certainly if G check is GLN, right? And in general, you say like it'll have some kind of minimal parabolic to which it reduces, and then the semi-simplification is like you induce to the VI, right? So if they have non-isomorphic semi-simplifications, then they belong to distinct connected components. So this is all setting. Okay, and then what this observation buys you, right? Since this thing breaks up into disjoint union indexed by the semi-simple local systems, we get similar decomposition for sheaf's node. Something falls out of this action immediately. It's already quite impressive, right? You know, we sort of want something like this in the arithmetic situation as well. Keep in mind, you know, these are really geometric local systems. Like I'm not assuming that they're fixed by the Frobenius or anything like this. There's going to be a lot of these. Okay, and then yeah, so that's corresponds to all automorphic sheaves. These side so that all automorphic sheaves. Yeah, we have this notebook seeing which all Hecke eigensheaves, including XXXVI. Okay, so some other applications of this action. Okay. Also use this action for the following. So one is that that's already, so a couple of these things I already alluded to. So one is that sheaves null is compatible generation. And kind of keyword here is valence of a spectral projector. Elaborated on later in the seminar. Okay, so this goes into the proof that this category is compactly generated. Another really interesting to be corollary to this is in the D module setting, the Rham situation. Okay, I can talk about arbitrary D modules, not necessarily like with regular singularities or anything like that. Right? And impose the nilpotent singular support condition, and then actually that implies that they have regular singularities. Which again is a little bit like the case where, like in BunG or something that had kind of a discrete set of K points, that would be automatic, right? So it looks like that again. And in particular, this implies that Hecke eigensheaves have regular singularities, which as far as I know was not. It's a condition on a D module, right? So it's it means that somehow the solutions kind of have polynomial growth, and most polynomial growth at infinity or something. So it has kind of an analytic flavor, but it's a condition on algebraic D module. So like BunG, for example, the exponential D module is like the classic example. It doesn't have regular singularities. Okay.
It's not.
Sorry?
It's not.
There's not a regular singularities. On like A1 minus 0, I have these D modules whose solutions are like next to the lambda or any lambda. Those guys do have regular singularities. Okay. So all of these nilpotent singular support guys and hence all Hecke eigensheaves automatically have regular singularities that follows from this action event. And then finally, the tensor product formula that I previously wrote. The fact that this thing kind of behaves well with respect to tensor product, also corollaries. I'd like to see a few more things. So, yeah. Any questions about this? Awesome. On. Finally get to arithmetic. Yeah.
Just want to make sure I'm sort of locating this correctly. There was this Monson before described this heuristic of Grinfeld's that like which I think might be just exactly this package, which is that somehow on the space of Langlands parameters, you consider
I'm about to come to it. I think.
Oh, okay. Oh,
yeah, I haven't
sorry.
gotten there,
In that
but
case,
yeah, you're absolutely foreshadowing what's about to
Okay,
come. So
sorry.
no, because we haven't gotten to the Langlands parameters yet, because these are really sort of geometric local systems, right?
Yeah, okay,
I'm about to get there.
yes.
All right, so the next thing, right? Arithmetic. So from now on, I'll write this is their notation for the space of unramified automorphic functions. And in particular, so one of the theorems from earlier, right, exactly said that this space is the trace of this Frobenius star acting on Sheaf's null. By the way, this isn't proved in the first long paper. It's conjectured there, and then it's proved in a subsequent paper. It's called like proof of the trace conjecture. This is what they called the trace conjecture originally, and it's proved after that. Again, kind of from the same circle of ideas. Okay, so this is sort of on the automorphic side. Now on the spectral side, we have the geometric Frobenius acting on X, okay, and that induces by transport of structure an endomorphism of Lopsis restricted. Okay, so important to keep in mind, this is not literally a Frobenius because this thing lives over Q bar. It comes by functoriality, right, from the endomorphism of X. Right? So this in turn allows us to define the stack of Langlands parameters. So this is what they call loxus arithmetic. And by definition, it's the fixed points of Frobenius acting on loxus restricted. And it's important that fixed points here is understood in the derived sense, okay? Because when you say fixed points, right, you're saying you have the graph of Frobenius inside of loxus times loxus, and I take the derived fiber product with the diagonal graph, right? So it's that sense of fixed points. So this is exactly what you would like to call the stack of Langlands parameters.
Our nice case is maybe it's the same thing as the last. You don't need to worry about 5%. At all.
It'll actually be highly derived, so it's something
Oh, I
that
see.
probably people, have been reaching for it for a while, and there's a few different competing definitions, like Shenwen Zhu has another definition, I think Schultz have proposed another definition, and Dennis says that they're all the same. I don't know if that's been written down, but there's several different candidates, and yeah, they're all expected to agree. But like I'll explain. So first of all, the 6 authors prove that this moduli stack of Langlands parameters is a derived Artin stack. So that already is not the case for loxus restricted, because I said it had these formal directions, and I'm saying this one doesn't actually. Frobenius somehow eats the formal directions, and it becomes a bona fide algebraic stack. Okay. Locally, here's some DAG mumbo jumbo for you. Locally, almost of finite type. I'll elaborate a bit on what this means. And but I should say in particular, part of the statement is that it's quasi-compact. Again, very much unlike loxus restricted, which had like many connected components, infinitely many connected components. This thing will have finitely many connected components. Okay, because sort of you should think there are only finitely many semi-simple local systems that are kind of arithmetic, right? And it is, however, not eventually co-connected, which is why I said almost a finite type. So what that means is that the structure sheaf is kind of unbounded below. It's derived, and actually the cohomologies go off to minus infinity. And you should think that means, in some sense, it's kind of highly derived. I mean, I don't know. I guess there are worse things in the world, but like this loxus restricted definitely was bounded, which follows from this fact that it's what's called quasi-smooth. So loxus arithmetic is what they call quasi-smooth. But such a thing is not eventually co-connected. So you should think a basic example would be like symmetric algebra on a single generator in degree -2. It's like that type of thing. Okay, and then now we can define, they call the algebra of excursion operators, and this is definitely in reference or homage to Lafforgue's work. So, namely, I take the structure sheaf. I mean, this is a well-defined algebraic stack. I can take global sections of the structure sheaf. I can take global functions. So this is some DG commutative algebra. Excursion, algebra of excursion operators. Again, this terminology is borrowed from Lafforgue. It's not exactly what Lafforgue defined. For example, this thing it does turn out to be connective, but again, it turns out to be kind of unbounded homologically below. As far as I know, it's not eventually co-connected. So it's definitely derived, is what I should say. And what actually the relation with Lafforgue's, well, he defines some classical commutative algebra of excursion operators, And so his sit in the following relation. One way to kind of summarize the difference is, first of all, Lafforgue excursion operators are not derived. Secondly, they kind of don't take the topology on the neighborhood. So what you can say is that there's a map from his classical algebra excursion operators to H0 of this derived thing, and it's surjective. You should think this is somehow huge and includes a lot of kind of nasty stuff. The topology on object. Questions? You know, I'm a little over time. I think I can do quickly. Okay.
So the hinges of what was the thing you said that bad?
Yeah, this looks like functions on kind of not necessarily continuous Langlands parameters.
I see. Okay.
It's classical kind of, I think, by definition, but it's
So it's classical at the expense of having a lot of jobs.
yeah. I mean, of course, you can extract the classical algebra from this thing as well by taking H2s.
I see. Is that a nicer algebra?
This thing, yeah, that's kind of what I'm saying. Is this is sort of what this thing wants to be, but it takes into account topology on the paper in some sense. Yeah. Okay, so now I need a little bit of abstract nonsense. Again, I will try to move through it quickly, but I think it just what I say will be unintelligible if I don't explain this really quickly. So there's something called the enhanced trace. This is the other kind of big piece of this formalism. So let's say A is a symmetric monodal DG category. And let's say I have a symmetric monodal endomorphism of A. You should think this is like quasi-co on a stack, and this is like the Frobenius. Pull back along the Frobenius or something like that. Then I can define the topological chains of A twisted by F. Okay. It sounds scary, it's complicated. So what I do is I take the tensor product of A as a bimodule over itself with itself. Okay, but for this second factor, I twist one of the module structures by F. Does that make sense? So A acts on itself, by multiplication on either side. I mean, the same because it's a commutative algebra, whatever. This comes from the multiplication map, right? And then I can also make A into a bimodule over itself in a different way, where kind of for one of the actions, say the left one, I apply F first and then. Okay, so it's twisted by F. And the fact that A was assumed symmetric monoidal, I could do this certainly for any monoidal category. I would have to write A reversed here or something, but otherwise it would look the same. But the fact that A was symmetric monoidal implies that this category of topological chains is also symmetric monoidal. It'll be symmetric monoidal just by contrariality, by some kind of general nonsense. Trace appears. So now let's say M is a module category that's dualizable as such. This is an additional input. And I'll have an endomorphism of M, which is compatible with F of FA. So that means it's not quite alinear, right? But it's alinear twisted by F. Does that make sense? Like if I act here, and then I act here by A twisting by F, it'll be linear in that sense. It's linear. So then this abstract nonsense, this so-called enhanced trace, produces the following kind of gadgets. So it's the, here's the notation, enhanced trace with respect to A, and F is also in the background here, right, of m twisted by fm. And what is it? It's going to be an object of this category of functional chains. Okay, so this is what this abstract nonsense buys you. And why is it called the enhanced trace? I had something called the trace earlier in a very similar situation where I just had an arbitrary and no functor of a DG category, and it was a vector space, right? So what does this have to do with the original trace? Well, it's actually a little hard to say in general, but it's easy to say what it is if A is rigid. So, compact objects are dualizable. Some more general notion. Let's say A is, if A were compactly generated, this would mean compact objects are dualizable. If A is rigid, then what you can say is that the usual trace of Fm acting on M is isomorphic to in the category of Hochschild chains from the unit into this enhanced trace. So hopefully this seems like kind of a reasonable, I upgraded the construction, right? So I have this vector space just for any endomorphism of M, okay? But in this situation where I have this extra structure, okay, I can actually produce an object of this category, it's a symmetric modal category. And I recover the original trace, this vector space, by taking hom from the unity. So you should think again in the case where like A is quasi-co on something, this will also be like quasi-co on something, and this will be like the structure sheaf, so this will be like both sections. So it's some kind of like upgrade of the trace to this more structured setting. Total abstract nonsense. And I just want to put this on the board because I'm going to apply it, and then you can just see how you can pattern. So that's all I want to do. Okay, so far so good. So just do the pattern matching part done. This is by far the coolest part, I think, is we'll get this really glorious kind of arithmetic application that recovers big pieces of Lafforgue's work and also refines it in sense related to this stuff. Okay, so back to our situation, we'll take A to be quasi-co on this restricted. We'll take Fa to be pull back along this Frobenius endomorphism of locus that I wrote down up there. In that case, this category of functional chains, this part is totally formal. You can prove that this identifies with the exactly the Frobenius fixed points of the stack. This is some general thing, in fact, endomorphism of the stack. Then its formalism will spit out the fixed points, quasi-co on the fixed points. So this is exactly going to be quasi-co on the system. Statement. And now we apply this enhanced trace construction to the case where M is the module sheaves null of BunG, which we saw earlier for very non-trivial reasons. A acts on M, right? And I'll take Fm to be Rob lower star, and we'll have to kind of believe for the moment there's natural compatibility between the two F's. It's definitely true. And so what this enhanced trace produces is an object, which they call Drinf. This object was anticipated by Drinfeld. I remember very clearly he was talking about this thing at that conference in Fry's electronics from 2014. Yeah, he discussed me
The original email in which we
yeah. Okay, so it's going to be the enhanced trace with respect to the action of this category of Rob star acting on sheaves null, which we just said a minute ago that that's exactly unramified automorphic forms. Wait, sorry, sorry, this lives, this lives in, sorry. Yeah, so if I did without the enhanced, it would be automorphic forms, but instead, the enhanced trace is going to live in the Hochschild chains of FA acting on A, right? Which is exactly quasi-co on the stack of Langlands parameters. So we get the sheaf on the stack of Langlands parameters from this nonsense. This is the thing that's anticipated by Campbell. And now that formula for the enhanced, the relationship between the enhanced trace and the original trace is also relevant here. Unfortunately, it doesn't literally apply because of the kind of formal directions that this Lossless restricted has. Quasi-coonic is not actually rigid. The structure sheaf will not be compact, which is just always the case for something that's like in scheme, but it's not a scheme. Okay, but you still have something very close to this. You just have to tweak it a bit. So quasi-co Lossless G-check restricted is not rigid. But nonetheless, we have the following formula. So you kind of want to say global sections of Drent on a stack of Langlands parameters produces the non-enhanced trace, which is automorphic forms, right? This is what you would want. Now, again, because this is not rigid, this is not quite literally true. I have to tweak this functor. Let me just call it gamma co. So this thing is the actual global sections functor. Well, yeah, let me just say this functor is equal to the pullback functor from a point to quasi-co. So here, yeah, which turns out to be not quite the same thing as just regular global sections, but okay. So it's some tweaked version of global sections of this object Drent produces automorphic forms. So this is really, really glorious, right? I mean, this is what Drent wanted. So Drent kind of localizes the space of automorphic forms onto the stack of Langlands parameters, which is a beautiful thing. I want to say one more thing, and I know I'm over time. Is it okay? Yeah. 5 more minutes.
Yeah, absolutely.
Oh, it's just as long as it would be a shame to get so far and not say this, right? So
Your time is the only thing that would be.
yeah, I know. So it's keep that minutes. Okay, so oh yeah, and just sorry. This also back to this quickly. So notice that this algebra of excursion operators, this is just global functions on Lossless arithmetic. So this acts by endomorphisms on Drent, because this is a quasi-coherent sheaf on that stack. So this commutative algebra of global functions acts by endomorphisms on this quasi-coherent sheaf. Therefore, right, using this isomorphism by functoriality, we get an action of excursion operators on automorphic forms. So this is what I was saying, kind of is very close to what Lafforgue proved. On the one hand, he proved this in much more generality because he worked with arbitrary, possibly ramified automorphic forms. On the other hand, this algebra of excursion operators is something that's a bit more refined than his version of it. So that's kind of the comparison. Okay, and then finally, the last thing I want to say is how to deduce something arithmetic from restricted Langlands. Okay, so far, this stuff is actually unconditional, right? As I said, the action, all I really used was the action of quasi-co Lossless restricted on automorphic forms, and that's, or on, sorry, on sheaves nil, that's unconditional. Now I'll say something that is conditional on the restricted geometrical Langlands conjecture. It's also very beautiful. So let's remind ourselves what it says, right? Sheaves nil on BunG is equivalent to intco with nilpotent singular support on looks that's restricted, equivariant for the action of quasi-go looks that's G-chip restricted. I didn't say this earlier because I didn't have the spectral action yet, and certainly this would be a desideratum of the conjecture, is that it's compatible with this action. Okay, and so what this spits out, the fact that I have this, together with compatibility with the Frobenius, there's a little tiny extra ingredient, which they're a little bit vague about in the paper, actually. I'd like to understand this better. But assuming that everything here is compatible with Frobenius, by taking categorical trace, okay, of Frobenius on both sides, the sort of two different versions of Frobenius, on the left-hand side, that produces unramified automorphic forms, right, by the trace conjecture, now trace theorem. On the right-hand side, well, what do you get? You get trace of Frab upper Schriek acting on this intco. Okay, so what the heck is that? Well, there's actually just a general formula for it, which my impression is that this is due to Dario Beraldo. This is intco global sections. Okay, a less kind of highfalutin way to say it is this is going to be global distributions on the stack of Langlands parameters. So it's intco global sections of the dualizing complex. And this is really amazing, right? I mean, this is this kind of completely explicit, in some sense, spectral expression for the space of automorphic forms. Something completely new, as far as I know. Now, if you kind of tried to guess naively what such a thing might look like, you might hope that you would have global sections of the structure sheaf, right? That I would instead have like excursion operators here or something like that. Now, that's not what we get. They're actually, omega is definitely not the same thing as O, which is related to the fact, like I said, that this thing is highly derived. So because O looks like it has cohomologies kind of going off to minus infinity, it's not eventually co-connective. This thing is not eventually connective. So this has cohomologies kind of in degrees going off to plus infinity. So this thing looks big and unbounded, but going off in the positive direction. So these are really bona fide different objects. Okay, and then the very, very last thing, really half a word, way over, just so much to say, is that kind of very closely related to this formula is a formula for Drenth. So first of all, this would be compatible with the action of excursion operators on both sides, right? Excursion operators will act here as well. And finally, one more thing that we would have kind of as a consequence of this, there's a functor from intco to quasi-co in all cases. And because locus arithmetic is not eventually co-connected, this functor is a little bit crazy, not maybe exactly what we expect it to behave like. If it were eventually co-connected, this thing would have a left adjoint, fully faithful left adjoint, for example, but it doesn't, so it's a little bit weird. So, but in any case, what we would get also from this picture is that omega maps to Drenth. So this is an explicit formula for Drenth, in fact. So I take this kind of, they call it unrenormalization in the paper, okay? And if I have an object of intco, the idea here is I represent it as a filtered colimit of coherent complexes, right? I transport that diagram over here, and then I take the colimit in quasi-co, okay? And that'll exactly produce this object Drenth. Okay, which is sort of, it's very, very close to this statement. You had this, for example, imply this, they're very close, like I said. Okay. So that's an explicit formula for Drenth, and that's the last thing I wanted to see. Thank you.
Any questions, comments? All right, hopefully it's not too loud, but